Okay, so now it's time to talk about isomers, right? Isomers are different compounds that have the same formula. In general, there are two types of isomers, constitutional isomers and stereoisomers. Constitution is really important that we appreciate this. Oh, you should pause the video now and get your model set out. Pause the video and get your model set out, all right? Because it's going to be, I think, key in you really getting a deep understanding of this. This needs to be easy for you soon. So, constitutional isomers differ in the order in which the atoms are connected. So when we first talked about isomers this semester, we said the example we gave was diethyl ether and ethanol, right? Where all these are hydrogens. Remember that? Was the very first example we gave, okay? So those are constitutional isomers. Can you see how these atoms are connected differently? All right, so those are constitutional isomers, okay? And stereoisomers now have the same molecular formula, but they differ in spatial arrangement of the atoms. And the next couple slides are dedicated to stereoisomers. I do want to point out before we move on, though, that there is one other kind of isomer which is not mentioned here, and it's some people would argue that it's not an isomer, okay? But we've already talked about with Newman projections, right? We've talked about something that's staggered, right? And something that's eclipsed, right? This is staggered. Remember this from a recent conversation? Staggered and eclipsed. And if these are all hydrogens or these are all methyl groups, are all the same thing, then this is as complicated as we can get. But these are considered, now watch this, I'm going to write the word out, and you should say it out loud. Conformational isomers, okay? I don't think there's any way to get really comfortable with this without building models and proving to yourself what these things are. So you should build models and you should space it out too. You should not attempt to do this all in one day. All right, so let's move on to a deeper conversation about isomers. Now, stereoisomers are two molecules, look, that have the same connectivity, but they are not the same, right? Look at this. Can you see here that these two methyl groups are on the same side of this six-membered ring, right? And so they're called cis for same side, okay? Now, if they're on the opposite sides of the ring, then they're called trans. Now, I encourage you, this takes some time, but you should stop the video now. You should build a six-membered ring, right? And if you're not used to your model set, even that's going to be difficult because there needs to be sp3 hybridized carbons, right? It's easily worth your effort, though, and I sincerely hope you'll do it. Stop the video, make a six-membered ring with sp3 hybridized carbons, make a methyl group on both on the same side of the ring, and prove to yourself that we cannot twist the bonds or rotate the bonds such that we can make it a trans. All right, so these are not the same thing. Cis and trans, 1,2-dimethyl cyclohexane. They have the same connectivity, but they are not the same compound. They have different physical properties, and so they are indeed different. All right. So let me think. I was going to say one more thing about this before I moved on. I can't think of it. All right. So I hope you'll build those and prove to yourself they are not the same thing. It's going to take some time. It's easily worth your effort. Now let's look at another kind of stereoisomer. There's a stereoisomer where we do not have free rotation around this bond because it's a double bond, right? It's got a sigma, one sigma, and one pi bond. So it's a double bond. We do not have free rotation about this bond. The reason why, remember this? We talked about this, I think, 2 chapters ago. We do not have free rotation about that bond because in order to rotate, right, this is an unhybridized p orbital, right? And here's another unhybridized p orbital. They're parallel, and so it makes a good overlap, right? It makes a good overlap here, good overlap here. So that's the pi bond. Here's the sigma bond, which we've just drawn as a stick down here, okay? So if we were to rotate this, we would lose that overlap, which would effectively be breaking the pi bond. What is that? I'll look at that later. That looks like some kind of little tiny animal there inside the slide. No idea where that came from. All right, so this is another example of stereoisomers. So one kind of stereoisomers we had were because of rings. How do you spell ring? R-I-N-G. Rings give rise to possible stereoisomers, and and pi bonds, which do not allow free rotation. Neither of these allow free rotation, and those give the opportunity for stereoisomers. All right, so let's look at a couple examples, and you tell me if these are isomers or stereoisomers, or the same thing. Okay, so you should pause the video and make a judgment about each of these. Okay, so I'm going to assume that you paused the video, and I am going to give you the answers now. These two are the same thing, identical, right? And they're actually conformational isomers, right? Because we had a ring flip. Can you see that if I flip this ring here, if this carbon goes into the up position instead of the down, or this is an equatorial right here, and this is an axial. You should be practicing all these names as you go along. You know they're going to be both on your midterm exam and your final exam. So it's the hydroxyl is in an equatorial position here and an axial position here, but they're not constitutional isomers and they're not stereoisomers. So they're identical, okay? Actually, whisper, they're really conformational isomers, but again, some people dispute that conformational isomers are technically isomers. All right, now what about this guy over here? So we have an equatorial and an axial, but importantly, they're both on the top side of the ring. And here we have an axial and an axial. And so these, these are stereoisomers. These were identical. These are stereoisomers because these are both on the same side of the ring, and these are on opposite sides of the ring, okay? These are not the same thing at all. They have the same molecular formula, I think. Watch this, 1, 2, 3, 4. C4, there's 2 hydrogens here, 2 hydrogens here, 2 hydrogens here. H8O, Oh, wait, these are constitutional isomers. Oh, yeah, of course. They have the same molecular formula, right? 1, 2, 3, 4. Yeah, I'm glad I was a little slower there. See how my notes saved me? Folks, that was a Freudian slip. That was, honestly, that was not a trick on my part. I really did not see that they were isomers at all. But when I made notes to myself, I was like, hey, wait a second. They have the same molecular formula. So, yes, these are constitutional isomers. Okay? Now, what about these? Okay, so this is hard for me to see. So what I'm going to do is I'm going to do a block and a block and a block, because the block tells my eyes these are all the same thing. They're all methyl groups, right? A block for a methyl group, a block for a methyl group, and a block for a methyl group. I can see that this methyl group over here is on the same side as another methyl group. And it's on the same side as another methyl group over here. These are the same thing. Do you see that? It just flipped in space. Okay, now let's do another one. Here's the bond which is not rotatable. Okay, so I'm going to do a block and a circle. That was an ugly block, wasn't it? Here's a block and a circle, and look at that. Do you see how the blocks and circles? I love notes. Notes made me famous. Look at that. The block and the circle are on opposite sides, and over here they're on the same side. So they would be cis over here, right? And they would be trans over here. Okay, so this is clearly a stereoisomer. All right, make notes, be like me. Good work. I hope you got the same answers. If you didn't, maybe you should stop and re-listen to that portion. See if you can see the differences, okay? Let's move on. Identify these. Now these apparently are cis or trans, and I'm going to identify these are cis, trans, or neither by doing block and circle. Okay, I can see the block and the circle are on the same side of the double bond. So this is going to be cis. Okay, block and block. These are both on the same side of the ring, right? Because this is equatorial and that's axial, and they're right next to each other. Another way to think of that is this has an axial position pointing down, opposite sides of the ring. So these are also cis, right? Okay, block, circle, opposite sides of the double bond. You see that? Opposite sides? That's trans. Boy, I think you're going to love making notes. If you make notes, you are going to love it. You're going to get good. It's going to be easy. Opposite sides. Trans. Block, block, and block. This is on the same side as that one, so that would be cis, but it's on the opposite side, so it would be trans. Wait, this is not a stereoisomer. Not stereo. It's neither. Okay? All right, so that's, I think, a thorough recap of what isomers are, but fast. So you're going to have to practice that. Get your model set out, practice it, make notes, make a test for someone else, and you'll get good at it. Good luck.